Hi, this is Silvia Mazzoni and welcome back to my videos. In this video series, I'm going to be benchmarking HDF5 format, which is an improved format for managing lots of data. No, not big data, lots of data. So let's get started. Of course, you know me, I'm going to start with the conclusions, which is really just to be able to give you an idea of why we're doing it and what we're doing. So what are we doing? Well, of course, I'm going to give you some of the basics about HDF5 format and just fundamental understanding of it. You can't benchmark something until you understand it. Then I'm going to do two types of benchmarking. The first type of benchmarking is going to be on data types. So different types of data that you can store in HDF5 format. This benchmarking is not to look at all data types, but two different options that you have for the application that I'm interested in. The other benchmarking is the structure. How do we want to structure the data and the files to optimize storage, performance, and use? Both of these benchmarking tests is something that I recommend that you do with your data. The structure of your data itself and the applications are different from mine. And so that's going to lead me to the recommendations that most important and think ahead in the design and testing of how you want to manage your data, because you've got to think about use, space, and time and performance. And these are all different metrics that are different depending on the different applications that you're looking for. So let's get started at the very end and looking at conclusions. So my conclusions are that I do think that HDF5 formats are great for storing and retrieving data, especially binary data. Not just any data, of course, but certain types of data lend themselves best to HDF5 format, and I will talk about what I mean by that. They're not meant for managing metadata, but I mean, they do store it. You can still store the metadata in your HDF5, but it's not like a database where you want to search the data and query it and do different types of managing and interaction between, magnitude and distance and different properties of your data set that you want to search. This is literally, and that's why I'm talking about storing data, not metadata. What's really nice about it, though, is that you can store metadata, you can filter on the metadata, but it's not quite as flexible as storing metadata, which is nice tables that you could store in a database format or simple dictionaries that you can store in a JSON format. The key advantage of using the HDF5 format is that when you're reading it or writing it, you're not loading the entire file contents into memory. Okay, in JSON, in CSV, or even in a database format, you're literally working with everything in memory. With HDF5, it's almost like a bucket, kind of like S3, where you go in and you grab only the data that you want. So this is not a database type of format. It's not where you be working with these different types of data. You literally need to go and retrieve data and use it. As I will show you in the studies, you have many options in designing your management of your data. And so think about it, do some thoughtful design ahead of time, make your choices ahead of time, and do this by testing your options and their scalability. And so it really depends on the type of data that you have and your applications, the size of the data, but also the shape of the data. And I'm going to show you the application that I'm going to be working with. This really fits in very well. And always keep in mind that sometimes you can get somewhere faster on foot than by car. You've got to make a decision of how to get there based on where you are and where you want to get to. Of course, we're going to start with some basics so that you have an understanding of HDF5. So HDF5 is, by the definition and its name, is a hierarchical data format, and I guess it's version 5 of it. It's an open source file which comes in handy to store large amounts of data. As the name suggests, it stores data in a hierarchical structure within a single file. Okay, so again, it's large amount of data. So doesn't have to be the big data, but maybe you can have lots of little files, which is really my concern, or I have lots of moderate sized files. An HDF5 is a container for two kinds of objects: data sets, which are array-like collections of data, and groups, which are folder-like containers that hold data sets in other groups. And so it's really nice. You can build a structure. It's a self-documenting object because you can actually query what are the keys, what is the content and what type of data do I have. So it's not just a table that you look at what the headers are. You may have different types of data at different levels, and you may have subgroups so that maybe things are grouped and organized. And I'm going to show you better graphics. So groups are like dictionaries in Python and other languages, and data sets are like NumPy arrays. Actually, NumPy arrays are the best thing to store in HDF5 format. This is a graphic that I put together of the HDF5 structure. I kind of looked at the web and got some ideas, and this is how I visualize it. This is the root folder, okay? This is where you enter your data set here. Okay, and you can see these are not, simple tables. They could be tables if you want. You could be storing lots of tables. And that's really the point of this, is that you're storing lots of tables of different sizes and different structures. You may have, groups within groups and subgroups. You may have data sets right there in your root folder. You can have them in groups, and then you can have attributes, which are like metadata. So it tells you information about maybe what are the contents of this folder or this file versus a different one. And that's something to keep in mind as well, is this is one object. Do you want to work with many objects, or do you want to have one big object? And that's something that I tested in this benchmarking. And so the simple graphic that you see here, you've got four basic concepts. The root folder, which is really just the entryway, so it almost doesn't count. Then you've got groups that are like folders, data sets that are data, and then attributes that are the metadata. And so you can kind of work through a path almost within your structure if you want to get to certain data sets. If you want this individual data set that is in group 1 of subgroup 1 of subgroup 2, you work your way and you can describe the path. So you've got subgroup 2 / group 1, group 1. And so as you see here, you see how I use the same names? And that's really the point. I wanted to use the same names in the substructuring so that maybe it makes some sense to you into what does each level represent. Okay, and again, that really depends on your application. So when to use HDF5 files? Well, first I'm going to tell you when not to use them, or maybe to look at a different option. If your data is, and remember I mentioned this before, it's all about shape. Okay, what is the shape of your data? If you have data that is nicely organized in tables, such as what you see here in the figure on the right, you've got columns of data. Maybe it could be metadata. If you're looking at earthquakes, this could be record information, could be site information, could be source information. So in that case, you may want to consider other more efficient storage options, such as Parquet, SQL, or CSV. I just learned about Parquet, and it's really, really cool because, well, I could do a whole video about Parquet. So if you have data that is held in tables, you may want to consider using other options. Now, the issue with other options, if you don't use HDF5, is that you would need a single file. Well, on a SQL, you can have a database, but you have a single file for each table. In HDF5, you could store this data, and heck, you could store all 3 tables within your HDF5. And that's really, to me, what the strength is of HDF5. And it's great if you want to store many different data objects of different types and sizes in one file. And it's great if you don't need to query the content, just the name and the metadata. And so here's an example here of, these are ground motion series. And that's really the application that I'm going to be using here, because that's what I've been working on with it. You've got, some earthquakes are short, some earthquake records are long, and some are mixed length. And so this is data. All I care about is this data itself. Maybe I might want to choose file 1 and file 3 because they belong to a certain earthquake. And maybe you can store what the PGA is, or maximum and minimum values of these data. But I don't need to search certain parts of this data. So if I'm working with tables, maybe you might want to query tables where you only want this part of this data, or only this part of this data because it meets certain criteria. Okay. In that case, you want to work with these types of, Parquet or SQL, even CSV. It really depends. And then you can do benchmarking on those different options. And it really depends on the resources that you have, as well as the languages that you're working with. In HDF5, again, it's about storing and structured data. And because you can store all these different objects, it becomes self-documented, because these, you can store them, the keys become the file names. You can organize them in groups. And so it becomes like a dictionary, and you don't need to predefine a schema. And so if you have a SQL, you always want to define a schema. What is the value or the type, data type for each column? In HDF5, you don't have to. So it's pretty much equivalent to JSON or XML, except for the fact that a JSON file, you have to load up the entire JSON. All right, same with XML. You want to read the whole thing and then parse it. Also with JSON, it's easier to write the whole thing at the end. Otherwise, you kind of have to append. While in HDF5, you can write things to it as you develop them. So it's much easier on your memory. Okay, so if you're dealing with, see, these are not very large files, but I have, millions of them. And so I would love to store them instead of individual ASCII files, to put them all into one or a set of HDF5. And this is what the benchmarking that we're going to be doing is, how do I want to store these data? Do I want to store them as strings, or do I want to store them as NumPy? And we're going to compare the two. And do I want to store them in groups, or should I just put them all in the root folder and let the keys be the file names, just be the keys? And so I'm going to be benchmarking these different options that you have. This is what works for my cases. Make sure that you test your case. Sometimes you've got things that are so simple that JSON may just be that much easier to go, and it's just that much easier to visualize, because JSON and XML can be read by humans. This is binary, okay? Big deal. Okay, it makes it more efficient, but it's binary. You can't just open up and understand it. You have to actually be, working through Python or some sort of interpreter to be able to open and read the file. While JSON, you double click on it, opens it up in Notepad, and you can kind of get a better understanding and a visual understanding. So this is great for humans. This is great for computers because it's self-documented, so you can write loops and read loops and things like that, so you can really get an understanding programmatically as to what's in this content, the contents of this file. Much more than you can in these, unless you look at the schema. Okay, so it's really important that you understand all these different options so that you know that you've made the right choice for the right applications. I'm working with CSV files. I also work with SQL and HDF5, and they're all different choices for different applications. One great feature of HDF5 format is its interoperability, which means that HDF5 files are just binary data objects. They can be read by any interpreter. You can read them in R, Python, MATLAB, whatever other program has written an interpreter for this data, which means that you can write an HDF5 file in R and read it in Python, or vice versa, which also means you can store the data somewhere and then others can access it however they want. You don't have to give an interpreter. You don't have to give them even a schema or anything like that. They can just open it easily in Python. For example, you can put it into a S3 bucket, and people can access it there if you make it public. So it's really cool, just the versatility of its interoperability. My main application right now that I'm going to be testing is ground motion time series. So storing ground motion time series I think, is one of the best example applications of HDF5 format. I have many individual files. Okay, I have a lot of these files that repeat. Okay, I have acceleration, displacement, and velocity trace. Okay, and this is what the files look like. I've got this little header at the very top that gives me important information, especially the number of points and the time increment. So I need this metadata, and then this is literally the time series. It's one long list that is written out in lines of 1, 2, 3, 4, 5 elements each. Okay, so the time series, actually, this gets converted into that. And interesting, you can't really just open this up in Excel. So it's nice how in HDF5 you can actually store it already formatted. Okay, so that's a step ahead. Right now, as I said, they're currently stored in individual ASCII files. Look, they're tiny little files, but I have tons of them. So I have a terabyte worth of these files. And so I would like to take them with me and do something with them. So here's a very important point to keep in mind though that I just learned is some of these files that I have are corrupted. Sometimes they were being transferred and maybe somebody stopped the transfer while this one was still being transferred. So that is the drawback with managing so many files because some may get lost. But if one file is corrupted, only this file is corrupted. If my HDF5 file is corrupted, everything is gone from that file because it's a binary file. So again, you got to weigh your options and see what's best. My recommendation is keep a backup. Now, as I said, for every acceleration time series, you also have a velocity and a displacement time series. You don't always use those because you can integrate the acceleration time series to get the velocity and displacement. But sometimes it's just easier to have them. Okay, the only difference between those files, the header is kind of the same, except for, of course, the units have been changed, and they just have a different extension. You know, some applications only need the AT2. Some people like to have all three. There's actually another format now that I've developed that has 4 columns, time, acceleration, velocity, and displacement in one table. And it's extra data, but some people like to have that already processed. So now I have 3 times or 4 times the number of files that I had before. And how do I want to store these? I can store them all maybe in one group that's going to have all 3 of these. And so that's one idea. Or maybe I should have 3 different HDF5 files, one for AT2, one for VT2, and one for DT2, because I'm not always going to need all 3. So again, that depends on your application and what you want to use. Why carry these additional data if you're not going to use it, or if you can compute it? And so again, you got to think about what you want to do. And in the benchmarking, that's what I'm checking. Do you have a performance difference if you have one file that has all of them, one file that has groups, and or 3 different files? And we'll compare the different options and metrics that we're looking for. We do have, what's really nice is each file does have a unique key. It has a unique record sequence number. The file name itself is the key. Okay, just like you have in a folder, so they all have to have separate names. Okay, it's important because then that helps you to, oh, I don't have to group them because they already have unique identifiers, the way I've set them up for NGA. The time series can then be stored either as a NumPy array or as a string array. Here's what you've got to think about, okay? And then you save it as a data set. Look at these data. I've got 1, 2, 3, 4, 5, I don't know how many decimal places I have, right? So I have 7 significant figures. So it's important, I don't need to store these as double precisions. I could store these as single precision. So now we're saving a little bit of space. Then the question is, if I had numbers such as 1.1 or 1.23, it may be easier to store these as ASCII or a string, or is it easier to store them as NumPy arrays with a bunch of zeros? Okay, and that's something that you've got to check and see if it's worth it. I do the check of comparison of NumPy versus string, but my application makes a difference because it is more than 3 significant figures in my numbers, okay? So then the NumPy definitely wins out. And what I'm going to do in this benchmarking is make sure you test, okay? So all I'm doing is a single degree of freedom analysis for each time series, and I compare the execution time and the results to make sure that I'm getting the same results out of the benchmarking. Always do that. Test your benchmarking data, okay? And so that's what I'm going to be going through. There's very simple basic steps that you do when you're working with an HDF5. Very, very simple, okay? You can either, and you don't even do all of them. You always have to open the file, whether you write or you read to it. So, and the only difference is write or read. You open it, you do something with it, and then make sure you close it, okay? And there's a way, depending on the language, that you could just have it in one command, you know, say, while this is open, then do these things. Then you're either writing to the file or reading to the file. Now, one important thing about HDF5 is that it does not dynamically allocate things. So if you remove objects from your file, you've used up that space. It won't recover it, okay? And so you don't want to use HDF5 files to be dynamically updated. It's literally to store data, okay? It's for storage of data. So there's different things you can do. You can create a group, and that's optional if you want. And it's just through a simple command of .create group and you gave it the group name. In my case, it's going to be the file name. Okay, or you can give it, this should maybe say group name. You can then, on that group, then you're creating, so this is like the main object. This is almost the root folder. So this here is this guy right here, okay? So then you can create a group, and that becomes its name, its binary name, and you've given it a label, okay? So this is the object. To that object, which is right there, you can then attach another group that even has the same name, but you see it's a subgroup to that. So now you created a group. So this is one group, and then you're actually going down to another group if you want to. Or you can add data set. So you can either create a data set right there at the root object, such as these data sets right here, or you can attach them to a group object. And then you just use the create data set and then the data set name. There's some additional parameters here, of course, you know, the data type, and if you want to do something beyond just the default values. But that's really all there is to the command, is those commands. And then you can assign attributes to either the data set, or you can even assign them to the root or to the group. So maybe this group could be called, you know, earthquake 1, and this is earthquake 2. Or this could be station 1 and station 2, depending on how you're grouping your data. And as I said, you can then assign attributes to the data sets itself. So maybe you could say this is, you can assign the DT, the time step for this data set, because we only have accelerations. You can assign the number of steps. You can assign a PGA. You can even say what earthquake this belongs to and what station this belongs to. And then you can search on these attributes. This is metadata, okay? And that's all there is. So those are the only really things that are in this file. And so you really have 3 main commands. In the read, it's kind of the reverse. So you can get the list of objects by asking for the keys, right? This is kind of like a dictionary, okay? And the formatting, what's really tricky here is this command here. How do you read the, you know, the data sets, or reading the attributes, or, you know, you can go from a group. And this kind of gets interesting, and look at, you know, the formatting on this. These commands here are in Python. Every language, if you're doing this in R, I had to do this in R, so I had to learn a different way of structuring in command. So different languages have different interpreters for the same data. But I did test it. I created a data set or an HDF5 file in R, and then I was able to read it in Python. The great thing about HDF5 is that it is platform independent. Once you've created this file, you can open it in whatever computer you're working with. You can even put it in an S3 bucket. You can open it, you can write it in Python, read it in something else. It depends on whether the language that you're working with has an interpreter. Python has it, R has it, and most everything else has it these days. And that's it. That's all there is to working with HDF5 files. The trick is just thinking about how you want to design your structure. You'll now become masters of HDF5. Congratulations for making it to the end of the first video on benchmarking HDF5 format, where I gave you an introduction and basics. I hope that this was helpful. Subscribe and click on that bell so that you will get the notice when I upload part 2 of this series, as well as part 3 and 4. Thank you. Bye-bye.